Hello and welcome back. In this lecture, we are going to discuss one more method to determine the particular solution. So in our last videos, we discussed about the undetermined coefficient method to find out the particular solution. And the method undetermined coefficient can be used. So suppose we have a non-homogeneous equation Ly equal to fx, and this fx is linear combination of finite products of following terms. It can be a polynomial in x, it can be an exponential function, or a sine cosine function. If we have this condition, if our fx is linear combination of finite product of these three, we can use the method of undetermined coefficient. And why only these three? Because we want something such that if we take the linearly independent terms of fx and its derivative, they are finite. Okay. In that case, we can use the method of undetermined coefficient. But suppose our function fx is not a linear combination of finite product of these terms, then what will we do? Then we can use the method of variation of parameters. And this method work in all the situation. There are certain integrals involved. If you can evaluate those integrals, this method is literally applicable to all the situations. Okay, so before explaining the variation of parameter method, let me show you an example for which method of undetermined coefficient doesn't work. So let's talk about y double prime plus y equal to 10x. Here our fx is equal to 10x, and if you list linearly independent terms involved in fx and its derivatives, then you will basically have infinite terms. Then the method of undetermined coefficient doesn't work, because using those terms we used to write our yp, but now we have infinite terms. So our method of undetermined coefficient fails. Method of undetermined coefficients fails. Then what we can do is we can use variation of parameters to find out our particular solution. And how we will do that, how variation of parameter method work, let me show you. So if suppose we have a non-homogeneous equation, in particular we are talking about the second order, so a naught x y double prime let me use the same notation. We used a2 for this. a1x y prime plus a0 x, a0 is a function of x times y equal to fx. Okay, we can find out the complementary solution. Suppose the complementary solution is given by c1y1 plus c2y2, and our y1 and y2 are linearly independent. Okay, we know how to find out complementary solution for constant coefficients, equation with constant coefficient. So suppose we find out yc, then our yp is going to be u1 y1 plus u2 y2, and here our u1 and u2 are not constant, they are function of x. They can be constant. Constant is also a function of x. So u1 and u2, these are functions of x, and u1 is equal to negative y2f So first we write down our equation in standard form. So we write down the equation as y double prime plus pxy prime plus qxy equal to fx divided by, okay, so our u1 is this and our u2 will be given by integration y1f divided by Wronskian of y1 and y2 dx. This is our method of variation of parameters. So what we are going to do is, we first find out the complementary solution, then we get y1 and y2, we find out the Wronskian, and using that Wronskian we will find out u1 and u2. Okay, so let's see one example. So let's start with the example we discussed before, where method of undetermined coefficient doesn't work. Y double prime plus y equal to 10x. So here the characteristic equation of our associated homogeneous equation is r square plus 1 equal to 0. It means r square is equal to -1. Take the square root both sides, we get r is plus minus iota. So our complementary solution is given by e power 0x. E power 0 is 1, so we are not going to write that. c1 cosine x plus c2 sine x. This is our complementary solution. Now you need to choose your y1 and y2. We want two linearly independent solutions, so we choose y1 and y2. These y1 and y2 can be any linearly independent solution of your complementary equation, of your associated homogeneous equation. You can choose y1 as cosine x, y2 as sine x, or y1 as sine x, y2 as cosine x, doesn't matter. Then we will calculate Wronskian of y1 and y2, which is given by determinant of first row. We keep the functions as it is, sine x, cosine x. In the second row we take the derivative. Derivative of sine x is cosine x, derivative of cosine x is negative sine x. So the determinant is going to be we multiply the diagonals, we get negative sine square x times, we multiply the diagonal minus we multiply the off diagonals, which is cosine square x. If we pull out the negative, we have sine square x plus cosine square x, which using the trigonometric identity sine square x plus cosine square x equal to 1, the Wronskian is negative 1. Okay, then we will calculate u1, which is negative y2f divided by w dx. y2 is cosine x, f is tan x, Wronskian is negative 1. Negative negative becomes positive, and we have cosine x times tan x. Tan x is sin x divided by cosine x. So cosine x cancel out. So this basically is integration of sin x dx, which is negative cosine x. Now we are not adding a constant of integration, though this is indefinite integral. We are putting our constant of integration to be 0 because we are looking for a particular solution. So we can substitute our constant of integration equal to 0. Okay. Then our u2 is y1f divided by the Wronskian dx. y1 is sin x, f is tan x, and the Wronskian is negative 1. Okay. So this basically is sine square x divided by cosine x. This I leave it to you to verify that this integration is going to be negative natural log of secant x plus tan x plus sin x. So we found out our u1 and u2. So yp is u1 y1 plus u2 y2. u1 is negative cosine x and y1 is sin x. u2 is negative natural log of secant x plus tan x plus sin x times cosine x. So this is your yp, your particular solution. If you want to write down the general solution, you can just write down y equal to yc plus yp and plug in the values of yc and yp. Okay. So what we learned is variation of parameter can be applied to any case. The general solution is given by u1 y1 plus u2 y2, where u1 is negative integration y2f divided by Wronskian, u2 is equal to integration of y1f divided by the Wronskian dx. This y1, y2 are two linearly independent solutions of your associated homogeneous equation. Okay. So this is how you find out your particular solution. So basically what we do is we find out the complementary solution, list our y1 and y2. Using y1 and y2 we find out the Wronskian, find out our u1 and u2. Then our particular solution is going to be u1 y1 plus u2 y2. And we'll stop here today, and in the next lecture we are going to talk about reduction of order. I'll see you in the next video. Till then, practice more and more problem for finding out the particular solution using undetermined coefficient and using variation of parameters. Bye bye, take care, have a good day.